Every time you flip a light switch, you're performing a tiny miracle. Think about it. Power, generated maybe hundreds of miles away, has to arrive at that exact instant. The whole system that makes this happen, the power grid, it's honestly one of the most complex machines we've ever built. It's this silent, invisible hero of our modern lives. So let's pull back the curtain and see how it actually works.
But that brings up a pretty obvious question, right? If this system is so amazing, why does it fail? Why do we still have blackouts? Well, the truth is, for all its power, the grid is constantly walking a tightrope. It is this incredibly delicate dance between how much power is being made and how much is being used. And even the tiniest slip can bring the whole thing down.
And here is the absolute heart of the challenge. See, unlike, say, water that you can store in a reservoir or goods you can pile up in a warehouse, you can't really store massive amounts of electricity. It has to be made at the exact same moment you decide to use it. That means supply has to perfectly, and I mean perfectly, match demand every single second across the entire continent. It is just an unbelievable balancing act.
So, to manage this impossible task, the people running the grid focus on two huge goals. The first one is reliability. You can think of this as the big picture question. Does the system have enough raw power to meet everybody's needs all the time? It's all about having the sheer capacity to keep everything humming along.
The second goal is security. And if reliability is about the big picture, security is all about what happens when things go wrong. Can the system handle a sudden shock, like a tree falls on a power line, or a big generator suddenly trips and goes offline? This is all about being resilient when the unexpected happens.
And this leads us to what is basically the golden rule for running the power grid, the N-1 contingency criterion. It sounds technical, but the idea is actually pretty simple. Think of N as every single piece of the grid, every power line, every generator. The N-1 rule means the grid has to operate perfectly fine even if any one of those major pieces suddenly disappears. The system has to be built not just for today's needs, but for today's needs plus a major failure.
And trying to meet that N1 standard? Well, that has been the driving force behind a century of innovation. The nervous system of the grid, the tech that senses problems and reacts, has gone through this incredible evolution, from these clunky mechanical switches to the super sophisticated digital brains we have today.
You can really see this evolution in 4 big stages. We started out with these electromechanical relays. They look like complex, whirring clocks. Then we got static relays that used early electronics. Then came numerical relays with the first microprocessors. With each jump, the grid got faster and smarter, which leads us right up to the 4th generation, centralized protection. And this 4th generation is a total game changer. It's called Centralized Protection, Automation, and Control, or CPAC for short. This is the moment where the grid really starts to get a single, unified brain.
Probably the best way to wrap your head around CPAC is with an analogy. Imagine an old substation was like an office full of individual, clunky computers. Each one did its own little job, and they didn't really talk to each other. CPAC is like throwing all those out and replacing them with one incredibly powerful central server. So instead of dozens of dumb devices, you have one coordinated brain running the whole show.
And the benefits of doing this are just massive. With a centralized CPAC system, everything is suddenly way more efficient. Changing settings is faster, maintenance is way simpler, and if you need to expand, it can be as easy as a software update. But maybe the most important thing is cybersecurity, because now you can focus on protecting one central brain instead of trying to patch hundreds of scattered, vulnerable devices.
So this is what that new architecture looks like. It's basically built in 3 layers. Down at the bottom, you have the process level. That's the actual hardware out in the yard, like the circuit breakers. In the middle is the bay level, which has devices that control one specific chunk of the substation. And then at the very top, you've got the station level. That's the CPAC, the big brain, watching over everything.
But, of course, technology never sits still. The next leap forward is even more radical. It's called Virtualization of Protection, Automation, and Control, or VPAC. Basically, we're taking the brain and moving it into the cloud.
So let's break that down. If CPAC was about moving all the intelligence from a bunch of little boxes onto one single physical server, well, VPAC takes the next logical step. It turns all those functions into pure software. The intelligence isn't tied to a specific piece of hardware anymore. It can run on pretty much any computer, just like an app in a data center. And the advantages of doing this are just huge. I mean, you get incredible flexibility, you're not locked into buying hardware from one specific company, and updating and patching your system becomes way easier. You're essentially future-proofing the grid's brain, making it this adaptable, software-defined thing that can grow and change.
But, and this is a really big but, this jump into the virtual world brings some serious new challenges with it. How can you possibly guarantee the split-second, real-time performance the grid needs when you're running on virtual machines? How do you defend against a whole new world of cyber threats? And how do you make absolutely sure there is zero delay, no latency, in those life or death messages? These are the huge problems engineers are tackling right now.
So whether a substation's brain is centralized in a server or totally virtualized in the cloud, its ability to keep our lights on really depends on three completely non-negotiable principles. Let's call them the pillars of trust.
The first pillar is redundancy. The philosophy here is simple. Never, ever rely on just one of anything. All the critical systems use parallel networks. So if one communication line gets cut, the other one is already running in real time. There is literally zero switchover time. The message always gets through, instantly.
Pillar number 2 is time synchronization, and the precision we're talking about here is just staggering. Every single device in the substation has to be timed together to within plus or minus 1 microsecond. That's 1/millionth of a second. That perfect synchronized timing is absolutely critical for the system to understand what's happening and make the right decisions in a fraction of a second.
And the final pillar, of course, is cybersecurity. As the grid gets smarter and more connected, it also becomes a bigger target. So its defenses have to be like a fortress. We're not talking about a simple firewall. This is a deep, multi-layered defense, all built on incredibly strict global standards designed to protect our most critical infrastructure.
So where is all of this incredible technology taking us? Well, the ultimate goal, the end game, is to create a fully autonomous, self-healing grid. A system that is so smart it can actually predict and prevent disasters before they ever happen.
You can actually see the entire journey laid out pretty clearly here. We went from old-school copper wires to fiber optics. Then we centralized the intelligence with CPAC. The next steps are all about artificial intelligence. First, we use AI to analyze problems after they happen to learn from them. But the holy grail is the final step, using AI to predict faults before they occur, letting the grid heal itself before you even know there's a problem.
And this isn't just science fiction. The research makes it pretty clear. AI-powered autonomous systems really are the future of how we manage the grid. They promise a level of efficiency and resilience that we couldn't even dream of a decade ago. We're talking about a system that can literally diagnose and heal itself.
And all of this leaves us with one final and pretty profound question. We are in the process of building this incredibly powerful, centralized, and increasingly autonomous intelligence that will run our entire society. So as this becomes a reality, we have to ask ourselves, who do we trust to control it? And how do we make sure that power is always used to keep the lights on for all of us?